Welcome to our exploration of LeetCode problem number 1565, titled None. In this session, we'll outline a general framework for approaching an unknown problem, focusing on key strategies and considerations. Let's dive in. The problem description for LeetCode problem number 1565, titled None, is unavailable based on the provided metadata. Without any details about the problem's requirements, constraints, or examples, it is not possible to generate a comprehensive slide. If additional information is provided, such as the actual problem statement or examples, I can assist further with a detailed explanation and analysis. Please provide any missing details or clarify if there's been an error in the metadata. To tackle an unknown problem, we can start by considering a general framework that applies to a wide range of algorithmic challenges. This framework includes brute force, optimized algorithms, and alternative strategies like greedy methods, divide and conquer, or dynamic programming. The brute force approach is often the simplest starting point. It works by exhaustively exploring all possible solutions. For example, if the task were to find the maximum sum of a subarray, brute force would calculate the sum of every possible subarray. While this guarantees correctness, it comes with significant computational costs, often resulting in time complexities like O(n squared, or even O(n cubed, depending on the problem. While easy to implement, brute force is impractical for large input sizes due to its inefficiency. However, it can serve as a useful baseline before moving on to more sophisticated methods. As we aim for more efficient solutions, optimized approaches come into play. These strategies reduce time complexity by leveraging mathematical properties, efficient algorithms, or specialized data structures. For instance, problems involving sorted arrays can benefit from techniques like two-pointers, which minimize redundant iterations. Dynamic programming is another powerful tool, especially for problems with overlapping subproblems, as it stores intermediate results to avoid repeated calculations. Similarly, binary search is a go-to method for efficiently navigating sorted data, reducing the search space exponentially. These optimized methods often bring down time complexity to O(n log n, or even O(n), making them suitable for larger datasets. However, they may require additional memory or involve more intricate implementations, which can be a trade-off when compared to simpler approaches like brute force. In some cases, alternative approaches offer the best solution. Divide and conquer is particularly useful for recursive problems, such as merge sort or finding the maximum subarray. This method splits the problem into smaller parts, solves them independently, and combines the results. Greedy algorithms, on the other hand, are effective when a problem's structure allows making locally optimal decisions that lead to a global solution. Examples include interval scheduling or Huffman encoding. Hashing and pre-computation are also powerful alternatives, especially for problems involving searching or frequency analysis. By using hash maps or pre-computed values, these methods enable quick lookups or eliminate redundant calculations. Each of these strategies has its own niche, making them valuable tools depending on the nature of the problem. The choice of strategy ultimately depends on the specific constraints, inputs, and outputs of the problem. For example, in problems involving arrays where optimized searching is required, techniques like two-pointers or binary search are ideal. For combinatorial challenges, dynamic programming or backtracking often provides an efficient solution. Frequency-based problems might benefit from hash maps or prefix sums. The goal is to balance correctness, efficiency, and ease of implementation. While brute force is straightforward and clarifies the problem's structure, it's often impractical for large-scale inputs. Optimized solutions, like dynamic programming, offer significant performance improvements, although their complexity can increase implementation time. Greedy approaches work well when the problem guarantees an optimal substructure. In summary, starting with a brute force solution can help establish clarity, while observations about constraints and requirements guide the transition to more advanced techniques based on the problem's specifics. When approaching any problem, the first step is to thoroughly understand its requirements. Begin by carefully reading the problem statement to interpret the input, output, and constraints. For example, determine whether the input is a single integer, an array, a string, or even a graph, and understand what the output should be. This could range from a single value to a more complex structure. Constraints are equally important, as they guide your choice of algorithm and data structures. For instance, an array size constraint like 1 less than or equal to n less than or equal to 10 to the power of 5 suggests that you need an efficient solution, while value limits may indicate edge cases to consider. Speaking of edge cases, think about scenarios like empty inputs, minimum or maximum values, and special cases such as duplicate values, sorted sequences, or cyclic structures. These details are critical in ensuring your solution is robust and handles all possible situations the problem might present. Once you understand the problem, the next step is to explore a brute force solution. Start with the simplest approach, even if it's inefficient. The goal here is to confirm your understanding of the problem and potentially uncover useful patterns or redundancies. For example, if the task involves finding a target sum in an array, you could iterate over all pairs to identify potential solutions. Similarly, for string problems, you might examine every possible substring. As you implement this naive solution step by step, take the time to analyze its time and space complexity. This analysis will reveal whether the approach is feasible under the given constraints or if optimization is necessary. Remember, brute force solutions often serve as a foundation for developing a more efficient algorithm. After implementing a brute force solution, the focus shifts to optimization. Start by pinpointing the bottlenecks in your initial approach. For example, nested loops might result in O, n squared, or O, n cubed, complexity, or you might notice redundant calculations that can be eliminated. Based on the problem type, apply algorithmic patterns to refine your solution. For arrays or strings, techniques like sliding windows, prefix sums, or hash maps are often effective. For graph-based problems, algorithms like BFS, DFS, or Dijkstra's might be appropriate. Optimization problems, on the other hand, could benefit from dynamic programming or greedy methods. As you refine your approach, it's important to iteratively test and analyze the optimized solution to ensure it's both correct and efficient. Writing modular code and leveraging constraints will help you maintain clarity and focus as you optimize. To tie everything together, let's consider an example problem: finding the maximum sum of a subarray of length k in an array. A brute force solution would involve iterating over all possible subarrays of length k and calculating their sums, leading to a time complexity of O, n asterisk k. However, an optimized approach uses the sliding window technique. Here, you maintain a running sum of the current window of size k, and as you slide the window one element at a time, you update the sum in constant time. This reduces the overall complexity to O, n. It's also important to handle edge cases, such as when the array length is smaller than k or when the array contains negative numbers or all zeros. By following this structured approach, starting simple, identifying patterns, and optimizing, you can systematically solve a wide variety of algorithmic problems effectively and efficiently. The problem statement for LeetCode problem number 1565 none is not available, which makes it impossible to implement a correct and complete solution. Without understanding the input format, output requirements, and constraints, it is not feasible to design an algorithm. The provided code serves as a placeholder and will need to be replaced with the actual implementation once the problem details are provided. This is the Java implementation of the provided placeholder Python logic. Since the problem statement for LeetCode problem number 1565 is missing, the code serves as a placeholder, returning a default message. Key differences include explicit type declarations in Java, the use of a main method for testing, and adherence to Java's standard class structure. In this example, we are tasked with finding the sum of all even numbers in a given list of integers. The input data provided is a list, 1, 2, 3, 4, 5, 6. To begin solving this, we initialize an accumulator variable, total_sum, and set it to 0. This variable will be used to keep track of the running total of even numbers as we process the list. With our input data defined and the accumulator initialized, we are ready to iterate through each element in the list and check whether it meets the condition of being even. We now process the elements of the list one by one. Starting with the first number, 1, we check if it is even using the condition number %2 == 0. Since 1 is not even, we move on. Next is the number 2, which is even, so we add it to total_sum, updating the total to 2. Continuing, we check the number 3, which is not even, so it is skipped. The number 4 is even, so we add it to total_sum, bringing the total to 6. Similarly, 5 is skipped as it is not even, and finally, 6, being even, is added to total_sum, resulting in a final total of 12. At this point, all elements have been processed, and the accumulator reflects the sum of all even numbers in the list. With the iteration complete, the final step is to return the value of total_sum. Here, the output of the function is 12, which represents the sum of the even numbers in the input list, 1, 2, 3, 4, 5, 6. Moving on to another example, let's consider the case where the input list contains only odd numbers. The new input data is 1, 3, 5, 7. As before, we start by initializing total_sum to 0 to track the sum of even numbers as we process the list. Looking at the state of our variables, we have total_sum initialized to 0 and the input data set to 1, 3, 5, 7. Now we begin processing each element of the list. For the first number, 1, we check if it is even, and it is not. The same check is performed for the numbers 3, 5, and 7, and none of them are even. Since no even numbers are found in the list, the value of total_sum remains unchanged at 0 throughout the iteration. After processing all the elements, the final step is to return the value of total_sum, which is 0. This output reflects that no even numbers were present in the input list. Now, let's consider a third example where the input list contains a mix of positive and negative numbers. The input data is -2, -3, 4, 5, -6. To solve this, we start by initializing total_sum to 0, just as in the previous examples. This variable will accumulate the sum of even numbers as we iterate through the list. At this point, the state of our variables shows total_sum as 0 and the input data as the list, -2, -3, 4, 5, -6. We are ready to process the elements one by one. The first number in the list is -2. Checking if it is even, we find that it is, so we add -2 to total_sum, updating the total to -2. The next number, -3, is not even, so it is skipped. We then check the number 4, which is even, so we add it to total_sum, updating the total to 2. The number 5 is not even, so it is skipped. Finally, we process -6, which is even, and add it to total_sum, resulting in a final total of -4. After processing all the elements, the function returns the value of total_sum, which is -4. This output represents the sum of all even numbers in the input list, including both positive and negative values. When analyzing time complexity, we aim to understand how an algorithm's runtime grows relative to the size of its input, often denoted as n. This growth is influenced by factors such as the size of the input, the number of operations performed on each input element, and whether the algorithm involves nested iterations or recursion. For instance, a single loop that processes each element once would typically have a linear time complexity, O(n). On the other hand, algorithms with nested loops might exhibit quadratic complexity, O(n², and those with recursion could even involve exponential growth, like O(2 to the power of n), depending on the depth of recursion. The key is to focus on the dominant terms as the input size grows larger, which is the foundation of big O analysis. However, since problem number 1565 lacks specific details about the operations or input, we cannot definitively determine its time complexity, as it would vary based on the requirements and the approach used, whether that's brute force or an optimized solution. Space complexity evaluates how much memory an algorithm requires as it processes the input. This includes the memory needed to store the input itself, any additional data structures used during computation, and, in the case of recursive algorithms, the memory consumed by the call stack. For example, an algorithm that uses no additional data structures might be considered in place, using O(1) space, while one that relies on an auxiliary array or hash map could require O(n) space. Recursive algorithms add another layer of complexity, as the depth of recursion directly impacts the memory used for function calls. Without specific details about problem number 1565, we can't break down its memory usage or classify whether it uses in-place techniques or additional storage. Like time complexity, the space requirements would depend on the problem constraints and the chosen algorithmic approach. Brute force solutions often involve systematically trying all possible options and, as a result, tend to have higher time and space complexities. For instance, an exhaustive search might require O(n²), or even O(2 to the power of n) operations, depending on the nature of the problem. Optimized approaches, on the other hand, aim to reduce these costs using techniques like dynamic programming, which minimizes redundant calculations, or binary search, which narrows down possibilities efficiently. These methods can bring time complexity down to O(n), or even O log n. Similarly, optimized solutions often require less memory by avoiding unnecessary data structures or leveraging in-place algorithms. In the absence of a concrete problem statement for problem number 1565, it's not feasible to directly compare the complexities of brute force versus optimized approaches for this specific case, but the general principle remains that optimization focuses on reducing both time and space overhead while maintaining correctness. When solving problems, it's common to make certain mistakes, and understanding these pitfalls can help you avoid them. One major issue is misunderstanding the problem statement. This often happens when key details, like input size limits or special cases, are overlooked. For example, missing constraints or edge cases might lead to inefficient solutions or even outright failures. Another common error is ignoring edge cases. Things like empty inputs, single-element arrays, or boundary values such as the maximum or minimum allowed input can easily trip up naive implementations, causing runtime errors or incorrect results. Overcomplicating the solution is another trap. Sometimes, candidates jump to advanced algorithms or data structures when a simpler, more straightforward approach would work just fine. Starting with brute force and iterating to optimize is usually a better strategy, as it reduces the chance of introducing unnecessary bugs. Finally, incorrect time complexity analysis can lead to solutions that fail under larger test cases. For instance, algorithms that scale poorly, such as O(n) superscript 2, might pass smaller inputs but break when the input size grows. Being mindful of these mistakes can greatly improve the quality and reliability of your solutions. Another common issue is failing to optimize space usage. This happens when unnecessary data structures are used or when you miss opportunities to modify the input in place if the problem allows it. Poor space management can result in memory limit errors or otherwise inefficient solutions. Now, let's discuss some key strategies for interviews. Recognizing problem patterns is crucial. Many problems fall into common categories like sliding window, dynamic programming, or binary search. Being able to quickly identify these patterns can save you a lot of time. It's also important to communicate your thought process clearly. Even if you're unsure about the solution, explaining your reasoning demonstrates your problem-solving skills, which interviewers value highly. Writing test cases for edge cases and verifying your solution step by step can help you catch mistakes early, which is another important habit. Lastly, be prepared to discuss trade-offs in your solution. For instance, a solution with better time complexity might require more space, and being able to articulate these trade-offs shows a strong understanding of the problem. To help build your problem-solving skills further, consider exploring related problems. For instance, the two-sum problem demonstrates the power of hash maps for quick lookups. Binary search teaches efficient searching techniques in sorted data. The maximum subarray problem highlights dynamic programming for identifying optimal subarray patterns, while the container with most water problem is a great example of leveraging the two-pointer technique for optimizing calculations. When solving these problems, you may also encounter different approaches, each with its own trade-offs. A brute force approach, for example, is straightforward and great for validating your logic on small inputs, but it doesn't scale well. Optimized iterative solutions, like sliding window or two-pointer techniques, significantly improve time complexity but require a deeper understanding of the problem. Divide and conquer methods are excellent for tasks like sorting or finding maximum subarrays, although they may require extra space and can be more challenging to implement initially. Finally, in-place modifications can save memory but might make debugging more difficult. Balancing these trade-offs is key to mastering algorithmic problem solving. That wraps up our session on a general framework for solving unknown problems. Remember to break down problems systematically and refine your approach iteratively. Thank you for tuning in, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!